All right, numbers 13 through 20 on our units 9 and 10 review. So our chi-squared and linear regressions. Now, I think I might have told you that you needed to put this in there, maybe a sample of 34 randomly selected adults. So that'll be needed here in a little bit, but let's go ahead and continue. Here at a computer printout, I can tell, of course, here is my sample slope. Here's my standard deviation of the slope. I'm going to be asked here in a minute to do the t-score and the p-value. Sample size 34, so degrees of freedom on this regression analysis is n minus 2. Here we go, find the t-ratio and p-value. For the test, null hypothesis beta is 0 versus the alternative hypothesis beta is not equal to 0. So right now, my brain is going, oh, look, I need to remember that this is two-tailed. I need to make sure I get that total p-value for two tails, okay? That should always cross your mind. Make sure you're careful on that computing whenever you see a two-tailed test. All right, so looky here. Here is our t-score, sample slope minus hypothesized slope of 0 over that standard deviation of slope. I got that as 0.4654, so 0.47. So then p-value is the probability of getting that sample or something more extreme. So I'm going to TCDF. So here I have this one tail. Here I am over here. My one tail's p-value, TCDF, get that cumulative area from 0.47 to 99 with 32 degrees of freedom. Well, that's a lot in that tail, which is expected because that t-score was just 0.47. So you weren't even a half of a standard deviation away from 0. Okay. But lo and behold, I remember, don't forget to double the tail p-value. So 2 tails worth of p-value is double that, 0.6416. So 0.642 is the two-tailed p-value. Very, very usual, very big. Here we go. Construct a 99% confidence interval. That's a panic. And yes, the conditions for inference have been met. So that's good. We do not have to R line, which is good because I don't have those all those graphs here. Remember that. I'm hoping I have all those graphs whenever we do that. All right. Beta is the slope of the relationship between pulse rate and height. Linear regression T interval is the name of what we're going to run. Oh, and we cannot run it in our calculator. But again, we're going to do our beta, sorry, not our beta, our sample slope, plus or minus that critical value here. Okay, so how am I getting this critical value? I need to be, again, 99% confident. So, okay, what's the common mistake? What's in this tail is not 0.05, but 0.005 and 32 degrees of freedom. So that critical value is negative 2.74. Got the positive and the negative of those, and then the standard deviation of the slope. Ooh, this is a very interesting problem. I'm glad this came up in this review because I wanted to really talk to you about this situation, and we had not seen it yet. So I was so glad when this came up. Okay, so look at this slope. This slope is estimated to be negative 1.24 to positive 1.82 degrees of freedom 32. Don't forget to state those degrees of freedom. So I am 99% confident that the slope of the relationship between height and pulse rate is between negative 1.29 and 1.82. They didn't give me units, but pulse is usually beats per minute, and then per inch of height. So I need to put those units in there for next year. But here's another way you could interpret this, more layman's terms. Hey, I'm 99% confident that for every additional inch height that a person is, the person's pulse rate could go down as much as 1.29 beats per minute or increase as much as 1.82 beats per minute. That's important. What's happening? I'm saying, hey, based on their height, you could have less pulse per minute or a lower pulse rate, or you could have a higher pulse rate. So therefore, that leads us to this next question, very appropriate. Do you think there is a predictive linear relationship between height and pulse rate? No way. That interval contains 0. If I were to run a hypothesis test, I'd anticipate failing to reject. I don't think I would reject that null hypothesis because, the slope could be 0. All right, which totally makes sense because do you remember that up above? Oh, yikesies, I put 0.321. The alpha, what was the p-value up here? Huge, 0.642, the p-value. I would not have evidence to reject the null hypothesis. So see, I wouldn't have evidence of a significant linear relationship. Okay. Now, number 16. Suppose that the researchers were hoping to just check out a positive linear relationship between pulse rate and height. So as you get taller, your height or your pulse rate gets higher. As you get taller, your pulse rate gets higher. And as you're shorter, you have less of a pulse rate. All right. Are the t ratio and p-value the same as in number 13? If not, what are they? Yes, the t-score is the same because I have the same sample results. But that p-value is not the same. A test for a positive linear relationship would just be investigating a one-tailed test, a one-tailed HA. And that one-tailed HA would just be one tail's worth of p-value. So the p-value would have just been 0.3208, not the two tails worth, which was the 0.6416. Okay. All right, so there's those problems. Very good question about that linear relationship. What happens when that interval has a negative and a positive? Okay. All right, number 17. What's the expected count for green peanut M&Ms? So that is this yellow cell that I'm wanting to find expected. And expected count is the row total times the column total divided by total. The first thing I did was I went 7 times 12 divided, okay, wait. And then I was like, what's happening? You need to total up those rows, total up this column. And then it did say there was a total of 207. So the total was 207. So there we had answer D. Number 18, appropriate degrees of freedom. Row minus 1 times columns minus 1. So that was 2 times 5. Degrees of freedom, 10. And number 13, okay. So let's kind of talk about the organization of this problem. So this problem had a random sample. When I went back and I read the prompt, it was a random sample taken from each type of M&Ms. So therefore, that was 3 separate populations, one sample taken from each population, each M&M type. Okay. So see, with that being said, then I know that's a chi-squared test of homogeneity. So that's my thought process. How is this organized? How many samples? Are they from different populations? Oh, yes, they are. That's homogeneity. So that means that this question is really posing, are these different populations, are these different kind of M&Ms having these colors at the same rate? So that leads me to what my HO and my HA are. So C says the color proportions are the same for all 3 types of M&Ms, and HA says the color proportions are not the same for all 3 types of M&Ms. So the rest of them are pretty easy to cross out. You may have wondered about answer choice A. Answer choice A says, it could be correct if it was just one sample, that the type of M&M and color are related or not. So the null hypothesis would have said there is no association. They are independent of each other. So A is a correct way to write a null and alternative if this was a chi-squared test of independence. Okay. The other three were all wrong, but because it's homogeneity, then C is correct. And our last one for this little video. Here we have that chi-squared statistic that I gave you of 22.9. So what then conclusion do you make? Well, I need that p-value. So I did my p-value from that 22.9 to 999 because remember our chi-squareds are all just upper tail. And there were 10 degrees of freedom. We had done that on, I think, number 18. So that's a very low p-value. So I need to reject the null. So there is evidence that the color distributions are not the same based on my hypothesis statements in number 19. Okay, so there's your numbers 13 through 20. Very interesting problems there and some good information for chi-squareds. And the interval, that was a very interesting interval with a negative and a positive in it. All right, I'll see you in the last video.